Hello and welcome to Calculus 1, Lesson 1B.1. Today we're going to learn about limits, graphically and numerically. Before we talk about that, I want to talk about a couple of things that we can do in a math class. Basically, everything that you do in a step to solve a problem should be one of these things. And all these things are either things that preserve the equality of an expression or preserve the relationship of an equation. So if you take any expression and add 0 to it, you haven't changed anything. And so you can say that your new result is equal to what it was before. Same with multiplying by 1 or replacing something with what it's equal to. I should switch these two things. Actually, I just put that one as number 5, I think. Whatever, we'll go with what it is for now. So 1, 2, 4, and 5 are all things that preserve the equality of a mathematical expression. It doesn't change the value or the weight, if you will, of what the expression is trying to say. When you do the same thing to both sides of an equation, you're not preserving the equality of each side, right? So if you're multiplying both sides of the equation by 3, well, each side of the equation is now 3 times as big as what it was before. It doesn't preserve equality, but it preserves the relationship of that equation. All right? I also want to call attention to 2 other terms that we use a lot in a math class: evaluate and solve. In calculus, we're going to need to know when to do one and when to do the other. It becomes especially important in calculus. Evaluating is any kind of rewriting, simplifying, computing, or plugging in. All right, so anytime you're crunching numbers or sticking a number into a function and getting an output, that's all evaluating. Anytime you're using order of operations or plugging things into a calculator to get an answer out, that's all evaluating. Solving, which I think is used too flippantly and too generally in a lot of math classes, but solving is specifically when you're trying to get a variable alone. You're manipulating an equation or writing everything in terms of a specific variable that appears in that equation. All right, so if you're thinking about a linear function, you might say, what is y when x is blah? That would be evaluating. If you're trying to solve it for y because you want it to be in slope-intercept form, that would be solving. Getting that y alone is solving. Or if you know y and need to find x, that would also be solving. And I'll flash these cards whenever I need to, whenever they're relevant. Okay, so onwards to limits. Consider the function x minus x to the third minus 1 over x minus 1. All right, Mr. Function, who are you and what do you do? You might notice that if you can remember how to factor difference of 2 perfect cubes, the top will factor like this. Okay, well, you should be feeling excited right now because we get to cancel something. And when you cancel, we're really just replacing something with 1 that is equal to 1, right? Whatever x is, x minus 1 over x minus 1 is equal to 1. And so what you've been told so far is that we can rewrite f of x as this friendly little quadratic right here. Well, guess what? You've been lied to. These functions are equal almost everywhere, but they're not literally equal. So maybe I'll replace this with a squiggle equal. So what do we want to say here? We want to say our function f of x is equal to x squared plus x plus 1 almost everywhere. there is an issue when x equals 1. And that's the one thing that those two functions won't agree on. Okay, this function, 1 is in the domain. Quadratic has a domain of all real numbers, right? Nothing's stopping you from plugging 1 into a quadratic function. But the original function can't do it. You'd be dividing by 0. We'll say f of 1 is undefined. Okay, because if you try to plug in 1, try to evaluate at 1, you're going to get 0 over 0, which is undefined. All right, so let's look at what's going on visually. Graph of this function looks like this. It resembles that quadratic almost everywhere, okay? If I plotted that quadratic, it would look just like this, except for that little guy right there. Right here, when x equals 1, there's a hole, or a removable discontinuity, is what we can call that. Okay, so at that one little point that they disagree, at 1, there's a little hole. But, I mean, come on, we can see what it's trying to do, right? What is that number right there? Oh, there's a 3 right there. Like that hole is infinitesimal, it's microscopic, it's only literally the number 1. If you go a little bit to the side, then you can evaluate that function all day, every day, nobody cares, right? So can't we just put our finger on that point right there and say the y value really wants to be 3? It looks like f of 1 wants to be 3. But just because it looks that way doesn't mean that we get to say that f of 1 equals 3. What we do get to say is that the limit as x approaches 1 of our f of x is equal to 3. So the function doesn't exist, it's undefined at 1, but the limit as it approaches is going to be equal to 3. In other words, when x is really close to 1, the y value, or the f of x, is really close to 3. What do I mean by really close? Well, numbers like this, that is equal to 1 as far as your naked eye is concerned, right? You'd have to pull out a magnifying glass or a microscope to see how that's different from 1 in most cases, right? But I could evaluate the function at that number. Okay, that number is really close to 1. So what I would get out if I evaluated the function at that number is going to be really close to 3. So let me pull out my calculator here, and with a little video editing magic, I get, ooh, my calculator says it's so close that it can't even measure the difference between that and 3. So to demonstrate this better, let me do it with fewer 9. There we go. So 0.999 plugged into that function evaluates to 2.997, really close to 3. So let me erase these down. 2.997. Okay, so we can imagine if x is sliding in towards 1 at these numbers that are really close. And we can do that from below, which is what this is doing, or you could think about numbers like 0.001, which evaluates to 3.003. Okay, numbers that are really close to 3. When I evaluate this function at numbers that are really close to 1, I get numbers that are really close to 3. So that's going to lead us to kind of a definition of what a limit is. Let's take the 1 and the 3 and replace them with variables, because we're going to talk about this for general arbitrary functions and not just this one. Okay, so if x is getting really close to some number c, while the y value is getting really close to some other number L, then we say the limit as x goes to c of f of x equals L. Geez, that's a lot of numbers, or a lot of letters there, right? So pick this apart a little bit. C is a number that x wants to be, but maybe can't quite achieve. And then L is what we imagine would happen to the function if x were actually allowed to be c. That's generally what it's going to be doing. However, we'll see that you can still do a limit in cases where the x is allowed to be c. We'll talk about that too. Okay, so f of c, actually evaluating the function at that c, may or may not exist. That c may or may not be in the domain of f. Okay, we can't evaluate functions at numbers that are not in their domain, but we can take limits and get close to it. And then f of c might exist, but could even be different from L. Evaluating the function could be different from what the limit is actually going to get you to. Now, when I teach this class in person, I'll actually pick on a student and I'll go up to them and I'll be like, I'm not touching you. Like, like you do with your brothers and your sisters when you're little. Like you're technically not doing anything wrong. You're not touching anybody, right? Like they said, don't touch me. Well, you're not touching them. You're just getting really, really close because you're trying to annoy them. That's kind of what a limit is doing, right? You want to annoy the person by coming really, really close to touching them, but without actually doing it. All right, so let's try another example. Find the limit graphically and numerically. So now we've got this function that wants to go towards 2. If I try to plug in 2, I would be dividing by 0. Because honestly, your first line of defense when it comes to limits is just try to plug in the x that it wants and see what happens. Sometimes you'll get your answer right there. Okay, in this divide by 0 situation, we got to do a little bit more sleuthing to see what's going on. So here's the graph. You pull out your graphing utility of choice, GeoGebra or your graphing calculator if you have one, or whatever you like to use. This is what the graph looks like. It ends up resembling a linear function. I'm assuming that however this factors, the x minus 2 is going to cancel out and you're going to be left with something linear. Okay, just like in the previous example, that looks like it wants to go to 1, right? So when the x is trying to be 2, the y is trying to be 1 because the coordinates of this point are 2, 1. This is another one where it has a hole or removable discontinuity. So we can say limit as x approaches 2 of this function is equal to the y value that it's trying to be, which is 1. And there's your answer. All right, now let's try a numerical argument. So we want to pick numbers that are close to 2. Trying to evaluate at 2 does not exist because it's going to divide by 0. Let's try getting close. Maybe we'll try 2.1, 2.01, 2.001, and 2.0001. And there's what happens if we evaluate that function at those numbers close to 2. Okay, for completeness, we should also do numbers that are a little bit less. So 1.9, 1.99, 1.999, but you get the picture. We're going to get numbers at like 2.0 something, right? Because those are also going to slide in closer and closer to 2 from that direction. Okay. There's your numerical argument. Let's look at another function. How about let's find the limit as x goes to 0 of 2x plus 3. This is a trick question in a way that, well, I don't need this fancy schmancy limit business to talk about this. I already know what happens at 0. I learned that a couple years ago. Why? Because we can evaluate that at 0. Right? There's nothing special about 0 as far as this function is concerned. The domain of this is all real numbers, including 0. So to find the limit of a function where the number you're approaching is actually something you can plug into the function, just evaluate it. Okay? There's no funny business. X wants to approach 0? Well, let it. There's nothing stopping it. So your answer here is 3. Okay, this one does have funny business. If x is 0 here, then you try to evaluate at 0, you get a 0 on top, and then you get square root of 1 minus 1, there's also 0. Get 0 over 0, and 0 over 0, that is funny business. Okay, so you could do this graphically or numerically, whatever method the question might be asking for. I'm showing the graph here so that we can see that as x is getting close to 0, we have a hole that shows that the y value is wanting to get close to 2. All right, so the graphical argument says, look at the graph and go, yeah, there it is. Numerical says, I'm going to guess and check numbers that are near what I want and see if I can figure it out from there. See if I can find out what it's trying to get close to. Now, sometimes that limit doesn't exist. Let's look at this function. We have absolute value of x over x. Okay, if I try to find limit as x goes to 0 of this function, I can't plug in 0 directly because that would make me want to do this. Okay, this method where we just plug it in and then it works out, this is called doing it by direct substitution. when you can evaluate the function at the value that it wants to approach, and you can get the answer that way. That's called direct substitution. So f of 0 does not exist. F of 2 is absolute value of 2 divided by 2, which is 2 over 2, and that's 1. F of negative 2, well, that's going to put a negative here. So now this is a positive 2 on top, and they're divided by negative 2, so it's negative 1. Similarly, f of negative 473 is also going to be negative 1. So when x is negative, f of x is negative 1. When x is any positive number, f of x is positive 1. But what's happening near 0? That's the interesting question. If you look at the graph of this function, what's going to end up happening is all of the positive numbers are evaluating to 1. All of the negative numbers are evaluating to negative 1, and 0 doesn't exist. It evaluates to neither. So what's going on here is if x approaches 0 from the right, y wants to be 1. If x approaches 0 from the left, y wants to be negative 1. And they don't agree. Okay, so in that case, we can say the limit does not exist. Right? So what does it mean for a limit to exist versus not exist? First of all, the notation that we're going to use is just put DNE. I wouldn't mark you off for putting an equal sign. It equals DNE, but that's a little awkward. DNE is not a number that something could be equal to. So just the statement, it doesn't exist, doesn't require an equal sign. Limits that exist, what do they look like? The function values have to agree whether you approach from the left or from the right. So they have to meet up in the middle. They might meet up in different ways, like that, or like that, but they've got to meet up in the middle and agree on where they're trying to go. It has to get close to a real number and stay close without any extra bouncing around. Okay, so if think about what trig functions can do. They bounce up and down between more than one value. Trig functions are going to give us an issue here. To get more precise about it, there's something called an epsilon delta definition of a limit. And I'll post a video in the description that'll take you through that. But it's more technical and more formal than what we actually need to understand limits at this level. If you go on to study real analysis or complex analysis, eventually you might work with the epsilons and deltas. This is something that you actually need to prove calculus, is working with those epsilons and deltas. What about not existing? Approaching from different numbers from the left and the right. So the one we just did, they're wanting to do this. They don't agree. When you come in from different directions, they do different things. You can also have increasing or decreasing without bound. So if you picture rational functions with asymptotes, doing that, or doing that, or doing like that, that would be limit does not exist. Or anything that gets crazy and wants to bounce around and oscillate. I'll show you an example of what that looks like in a minute. I know it's hard to picture at this stage. Okay, so the one we just did, we can say the limit does not exist because that function has this going on. They don't agree. They want to go to different places. Here's an example of increasing or decreasing without bound. Okay, in this example, trying to evaluate at 44. Evaluate at 44 would ask you to divide by 0, which is funny business. Can't do it. Okay, but when x gets really close to 44, you have this asymptotic behavior. Okay, when x is close to 44, the difference between x and 44 is a very small number. And dividing by a small number gives you a big number. So it really blows up as you get close to 44. When you're below 44, that difference is negative. So it blows up in the opposite direction. Okay, and remember, it still would be does not exist if it were both going up like that. Now let's talk about this guy. Sine of 1 over x. Well, remember that sine of theta is always between -1 and 1. And by the way, this that funky looking E, that's the element symbol. If I say that a number is an element of something, it just means it's in there. If I were to say alpha is an element of 0 to 1, for example, that means the same thing as saying that alpha is between 0 and 1, like that. So the element symbol says it's a number that is somewhere in the set that I'm referencing here. Okay, so whatever theta is, sine of some number is always between -1 and 1. So it feels like maybe this limit is possibly going to exist because it's got those bounds, right? It can't blow up. We know we're not going to get this kind of behavior. The problem is x isn't allowed to be 0 in there because you would be taking sine of 1 over 0, and you can't do that. But what happens as it's trying to get close? Here's our graph. And this is the crazy oscillating that I was talking about. If I look at any particular interval, here I can very easily see -0.2 to +0.2. Okay, if I take any interval around 0 like that, there are infinitely many places where the function value reaches both 1 and -1. Right? That's going to continue no matter how far I zoom in. Look at that. It colors it all in green because those points are getting so close that they're on top of each other. Isn't that nuts? So as x is approaching 0 here, you are evaluating sine at huge numbers. Okay, so as x is approaching 0, let me write this down for you. As x goes to 0, 1 over x gets really big. Okay, and so it's 1 over x is going to be traveling along the real number line towards the right, going faster and faster and faster. But you take the sine of that, and it's going to keep oscillating up and down. So it never gets to any particular number and stays there. So if we look at any interval around 0, such as negative 0.0001 to positive 0.0001, there are infinitely many x's in there that reach 1 and infinitely many that reach -1. So as x is approaching 0, this function is just bouncing around up and down all crazy. It never settles. It's okay if it bounces around for a little while, as long as it eventually gets to where it's trying to go. Okay, there's no specific point close to 0 where that function seems like it wants to be. So that's this example here. That's getting crazy and bouncing around or oscillating. So this is also does not exist. Right? So infinitely many mathematicians walk into a bar. The first one says, I'll have a beer. The second one says, I'll have half of a beer. The third says, I'll have a quarter of a beer. The barman pulls out just 2 beers. Mathematicians are all like, that's all you're giving us? How drunk do you expect us to get on that? And the bartender says, come on, guys, know your limits. And there we have it. Now we know something about taking limits graphically and numerically. Keep practicing and have a wonderful day.